Hi, welcome to another presentation. This one deals with probability. Now there is some prior knowledge that I'm expecting you to have, and that's a simple use of fractions and decimals and percentages, and an initial understanding of the idea of probability and how you calculate simple probabilities. So let's kick off straight away then with some examples, because that's often the best way of illustrating a method. Right, an old favourite, 52 playing cards. What's the probability that it's a diamond? Well, these are just initial probability type questions, so let's just dive straight in. If there's 52 cards and the diamond there are 13 of them, then you'll recall that the best way of representing it is in fraction form. So 13 over 52. Another way of thinking about it, there are 4 suits, so a quarter of the pack must be diamonds. Not a diamond. Well, this introduces the first property, if you like. What we're going to do is I'll make certain statements as we go along. So if you know the probability that an event happens, the probability that it doesn't happen is 1. Take away that probability. So the probability of not a diamond is 1 minus a quarter, which is 3/4. So what I'm using there as a rule, if I put it over here more formally, the probability that an event A doesn't happen, and that's standard notation, it's sort of like the complement notation if you have dealt with sets. The probability that A doesn't occur is 1 take away the probability that A does occur, whatever A might be. What is the probability that it's a 3? Well, how many 3s are there in a pack of cards? There are 4 of them. 4 over 52. Always simplify your fractions. I will qualify that when we come to tree diagrams. Don't simplify maybe until the final answer that you're looking for. We'll make that clear when we get there. 113. A red 3. Now it's red, but it's also a 3. And there are 2 of those, the hearts and the diamonds. So 2 over 52, which equals 1 over 26. The jack of clubs, well, there's only 1 of those, so that's 1 over 52. It's far easier to do these questions as fractions rather than turn them all into decimals. Last part then. Find the probability that it's a black jack, queen or king. Well, there are 2 black jacks, so the probability of a black jack is 2 over 52. The probability of a black queen, 2 over 52. The probability of a black king is 2 over 52. That's more likely than just being a probability of a black jack. We add these 3 probabilities together because we're relaxing the criteria, if you like. It can be a black jack, it can be a black queen, or it can be a black king. So it's more likely. What we're looking at here is 3 different situations that cannot occur at the same time. When they can't occur at the same time, they're called mutually exclusive events. Again, more formally, the probability, let's just talk about 2 things. The probability of A or B occurring is the same as the probability that A occurs added to the probability that B occurs. This only applies for mutually exclusive events, because if it's possible that both events could occur together and we just added them, then part of that probability we've counted twice. Thinking about it again in set form, which we will come to shortly, if you've got 2 sets that represent 2 separate events, this statement here only applies if the 2 events don't overlap. In other words, no intersection. So back to this question. we get 6 over 52, which we need to then finish off by saying that's 3/26. Another common way of representing your probabilities is in what's called a possibility space diagram. Among other things, it's a logical, systematic way of making sure that you've included all possible outcomes for a given question. So let's look at this example here. Two dice, or cubes, whatever you want to call it. Why is it die? Why is it dice? No idea. The words have been in use since the 14th century. I'm not really that old, so we'll just go with cube for the minute. 6 faces. One of them has got odd numbers on, the other's got even numbers on. So the gaps in the table represent the totals of the two values. So let's fill them in. Right, there we go. So straight away we can see that there's 36 possible outcomes. It also means that if we've missed one, if you were making a list, it would be easy to repeat a pair of options without realizing it, or even just miss one. So in a table, it's obvious there's a gap, then you've missed something out. So let's have a look. What is the largest possible score and the probability of scoring it? Well, now we've got everything filled in, we can see the largest possible score is 23. And the probability of scoring it, well, it only occurs once, so it's 1 over 36. Smallest possible score is the other end of that leading diagonal. Smallest score is 3. And again, that's equally likely, 1 over 36. What is the probability of an even score? Do we see any even scores in there at all? No, we don't. So probability is 0. What is the probability of a score less than 15? It's anything in this column. Oops. It's those 5. It's those. It's those. It's those, and it's that one. And it's doing weird things to the formatting in the cell, but never mind. There's 21 there, so that's 21 out of 36, which we know simplifies because they're both multiples of 3. That's 7/12. Another good way of illustrating what's going on in a probability question would be Venn diagrams. I'm going to use my maths to illustrate this because the diagram is going to be neater than my version. So I've chosen the A-level option, I've chosen the Stats 1 module, and I've gone for the revision section, or the revision lesson. So let's bring this problem up. 80 children took part in a survey about chocolate, milk, plain and white. You can see 3 overlapping sets already drawn onto the diagram. Now the thing with a Venn diagram, you can actually put numbers into it, which is what we're going to have to do here, but also if you're given information about probabilities, they could go into there. A Venn diagram doesn't just have to represent the elements in a set, it can be the numbers in a set or even the probabilities that a certain person is in a given region of the diagram. So let's start in the middle. That's always the best way of approaching these sort of problems with Venn diagrams. Start with the overlap of all 3, or the intersection. 18 like all 3, 24 like milk and white. Well, we've got 18 already, so there must be 6 in there. 3 like milk and plain, but not white, so that is a specific region. If it didn't say the but not white, then that wouldn't make much sense, would it? 24 liked plain and white. 18 of them are accounted for, so again, another 6 there. 31 like plain. So if 31 like plain, how many have we already got accounted for here? 27. 27, so there must be 4 in there to make 31. 38 liked white. Well, we've got 18, 30 altogether, so there must be 8 there. And 5 didn't like chocolate. So let's see how many children we've already got accounted for in the diagram so far. That's 50 children accounted for in the diagram. So there must be 30 here that only like plain chocolate. So the way it might be phrased is it might give you this information and say find the probability that a child is picked at random, find out if they only like milk chocolate, for example. Well, we can see that it's those 30 out of 80, or 3/8 as a percentage. Let's look at another one of these. 21 in a class, 10 learn French, 6 learn French and German, 6 learn neither. So let's put the information on a Venn diagram. Here we've got French, here we've got German. 6 learn both French and German, and we know that 10 learn French altogether. So that's the 10 accounted for. We don't know how many learn German only, but we know that 6 learn neither. So altogether we've got 16 accounted for. So that means there's 5 left, making the 21. So there's 5 pupils only learn German, so the probability of German only is 5/21. That's this answer. Taking this off on a little tangent, there is a branch of the branch of probability that you pick up at A level called conditional probability, and that might ask something like what's the probability that the pupil studies French given that they study German. So we know how many study German. There's 11. So if the question was what was the probability that they studied French given that you already knew they studied German, that narrows our class of 21 down to only these 11. So the probability that they learn French given that you know they're learning German already would be 6 out of 11. That's going beyond what we need at this point, just to show you that this sort of problem can be extended. Before we go any further, there's another term that we need to mention. We've already talked about mutually exclusive events being things that can't happen at the same time. Another word that crops up a lot in probability studies is independent. That is, events that are independent, that don't affect each other. Again, thanks to my maths and particularly Alan Jackson who set this page up. Independent events are things that don't affect each other. So throwing a coin and rolling a dice, for example, a die. The outcome on one won't affect the outcome on the other, or even in fact rolling a die more than once. Having got a 6, that doesn't change the probability that the next roll is a 6 as well. So when we've got independent events, we've talked about the OR rule for mutually exclusive. For independent events we have something called the AND rule. Namely, if you know that 2 events A and B are independent, the probability of A and B occurring is just the product of the 2 separate probabilities. This brings us quite nicely on to tree diagrams, which is a favourite on the GCSE papers, and that's a way of illustrating lots of different situations. We can represent both dependent and independent events on tree diagrams, and when we start drawing a diagram in a minute you'll see that branches that come from the same point are all mutually exclusive. So it's a wonderful diagram for representing lots of different situations. Having said that, they can become very, very unwieldy very quickly. Ideally, therefore, two different mutually exclusive events and up to 2 or 3 different experiments, if you like. But if we've got 2 events and then 2 separate experiments or 2 different things going on, then the end of the diagram will have 4 branches. If we've got a third set of events happening, then we're up to 8 branches. So you can see very quickly the number of branches you need to draw on your diagram can get very unwieldy. And if you're only answering 1 or 2 parts of a question, a big proportion of your diagram isn't being used. So how do we use it? As we go through, as we follow a path through the diagram, what we're actually dealing with are events that are either dependent or independent in a particular case. But if we follow the path through, we multiply the probabilities that we meet together. If the problem we're trying to solve results from several different paths, several different mutually exclusive outcomes, we simply add those results together. So going back to what I said earlier about simplifying your probabilities, if the problem you're dealing with has to involve adding fractions together, it's much better to leave them all in common denominators, which is what they will often be with a tree diagram. Don't simplify simple separate parts, because you're only going to have to put them over a common denominator again if you have to combine them. So rather than talking in generalities, let's try and pick up a particular example here. The key thing to do is to look at a question and see if individual events are relating or affecting each other or not. I'll do another example in a moment dealing with dependent events, but here, regardless of whether you feel like the traffic lights are all against you, then we can assume in this particular question that the first set of traffic lights and the second set of traffic lights are independent. The probabilities are different, but let's assume that they're independent for the sake of this question rather than over complicating matters. So the probability that the first set is green when he reaches them is 3/5. So on our diagram we put the 3/5 here, because that's the probability that the first set will be green. Now if the first set isn't green, we're calling it not green, because again we don't want 3 separate outcomes, amber and red. That must be 2/5. Going back to one of the first properties we talked about, the probability of something not happening is 1 minus the probability that it does. And notice that these come from the same point and they're mutually exclusive. So that's the mutually exclusive aspect of a tree diagram. Branches from the same point or node. The probability that the second set is green is 2/3. And so not green is 1/3. Now these second set of branches are the same repeats here. All we're doing is we're repeating them down here because we're attaching them to a previous event. So those remain the same. Occasionally a question's worded whereby, depending on what's previously happened, these might be different. So that's our tree diagram complete. If you have to draw one from scratch, or as is often the case, the branches are filled in but everything else is missing, it's vital that you label the branches as well. If you just put the numbers in, not only might it confuse you, it's going to lose your marks in an exam if you don't label things properly. Now let's have a look at what it's actually asking for. Find the probability that he has to stop at both sets of traffic lights. So here we're talking about the probability of not green and not green. So this is where the AND rule comes in. It's the 2 separate probabilities multiplied. So it's 2/5 and 1/3. And that we can simply write as 2/15. Part B. This is another one of those sort of beautiful aspects of probability trees. Just one set of traffic lights is green and the other not. Now, if you're not careful and you didn't do it via a tree diagram method, you might be tempted to miss out one of the options, because if it has to stop at just one, that means the first one could have been green and the second one not. Alternatively, it could have been that the first one was not and the second one was green. So we've got two separate mutually exclusive outcomes. So we've got green followed by not green. That means he stops at the second set. Or we've got the probability that he stopped at the first set of lights but could go on at the second. So that corresponds to 3/5 times 1/3 added to 2/5 times 2/3, which equals 3/15 plus 4/15, 7/15. Now this last question, there's two ways of answering it. At least one set of traffic lights. He has to stop at least one set of traffic lights. Means he could be green first, followed by not green. Not green, followed by green. But at least one means both as well. So one way of doing it would be to add up three separate multiplications. A quicker way of doing it would be to realise that that's one, take away that option that it doesn't include. If both sets of traffic lights were green, he wouldn't have to stop, and that's the only one that doesn't form part of the solution to this answer. So 1 take away the probability of green, green. So whenever we get an at least, it will invariably be most of the branches, if not all but one, in which case a quicker solution is to subtract the one that it doesn't include. So it's 1 take away 3/5 multiplied by 2/3, which is 1 take away 6/15, which is 9/15. And we can simplify this down. 3's into the top go 3, 3's into the bottom go 5. Right, here we've got a case where the second set of branches, which represent the second chocolate being pulled out, are dependent on the first ones. So there is an element of conditional probability here. I mentioned it being an A-level topic, but in a situation like this, it's very much a GCSE situation, and a tree diagram is the best way to go. So a box of chocolates with 10 chocolates with hard centres and 15 with soft. So we've got 25 chocolates and we've got 15 25ths are soft, 10 25ths are hard. Now, if the first one taken is a soft chocolate, soft centre, he's eating it, he's not putting it back, so for the next set of branches we've only got 24 in the box. If he's eaten a soft centre, there are 14 left. If he's eaten a soft chocolate, soft centre, there are still all of the hard centres, but there's still 24 total now. The hard centres, there were 10 of them. Coming along this branch, if he's eaten a hard centre, there are still 15 soft centres left, but there's 24 altogether. If he's eaten a hard, there are only 9 hards left out of 24. So all of these probabilities here, in the definition of the word conditional that I used earlier, these are conditional probabilities. So we could say, what's the probability that the second one is soft, given that the first one was soft? It's 14 over 24, or alternatively 7/12. Another type of problem where you've got to be careful with the second set of branches is if it's something being drawn out of a bag and not replaced. Always look in the wording of the question as to whether it's implied or stated explicitly whether the second set of branches, the totals have changed or not. So let's have a look. I've put on the end of here the situations that going along that branch represents. So both chocolates having a soft centre, so the probability of soft followed by soft is 15 over 25 multiplied by 14 over 24, which I will simplify at this point. That's 3/5 multiplied by 7/12. Now I can cancel down here because I'm not doing anything else with this answer. 3's going to that once, 3's going to that 4 times. So the probability of pulling out a soft-centred sweet followed by another soft-centred sweet is 7/20. One of each kind being eaten. Well, that's a soft sweet followed by a hard sweet. Alternatively, it's a hard sweet followed by a soft sweet. So again, it's going to be the sum of two mutually exclusive outcomes. 15/25 multiplied by 10/24, and this one is 10/25 multiplied by 15/24. You can see that the numbers on the top are just reversed. So to speed up, you can often just write one down, but then double it. So we need to add these two together. I could simplify both of those, but as I've said before, we need to add them, so I'm going to leave them as the same denominators. So what I get is 150 over 600 plus 150 over 600, which is 300 over 600, which is a half. And lastly, at least one is a soft centre. So if at least one is a soft centre, that's going to be all those three options except for two hard centres. Well, two hard centres is 10/25 multiplied by 9/24, which in turn simplifies down to 2/5 multiplied by 3/8, which is possible to cancel further into 3/20. So the probability of at least one soft centre is 1 minus the 3/20, which is 17/20. Okay, that's me finished. I hope you found that useful. Don't forget there's loads of great websites out there. Here's just one example of maths on the BBC Bite Size website. There's a few reminders there about independence and mutually exclusive. Thanks for listening. Thanks for watching. I hope you found it useful. See you again soon.